If you're new to electronics, you might find transistors and other semiconductors to be slightly intimidating. What do they do? How do you use them? How do you detect the faulty ones? And how to understand the circuit. If that be the case, this video is for you. Hello friends, welcome back to the bench. Today we're gonna learn a little bit about transistors. This is gonna be a series, so we're gonna start slowly and we're gonna start from the perspective of a technician. We just want to understand how transistors are used in the circuits so we can understand the circuitry. Therefore, we can know how to diagnose when something goes wrong with it, where to look and how to measure. For this purpose, we're going to use a simulation software. In this case, I'm using LT-Spice, but there's plenty of other solutions, the ones that you can install or the ones that you can use online in your browser. You don't have to install anything. Some even visualize the current flow very nicely. Being able to simulate the transistor will allow us to understand how it works and how the circuits that utilize transistors work. This is the symbol for the NPN transistor, which has three connections: collector, base, and emitter. As the name suggests, collector is what's going to be collecting current, emitter is what's going to be emitting current. And that flow is controlled by the base. The current flowing from collector to emitter will be proportional to the current flow from the base to emitter. That's how this particular type of transistor works. First type of transistor we're going to be talking about is an amplifier transistor, 2N2222. Very easy to remember, just all 2's and an N. It allows 600 milliamp current flow from collector to emitter with maximum voltage of 40 volts. It also reacts in less than 20 nanoseconds, which can be used as an amplifier, it can be used as a switch. Here we have the first example of transistor being used in this circuit. As you can see, we have a power source, which is V1, which produces 10 volts. We have a current limiting resistor R1, which value is 100 ohms. And we have our Q1, which is our switch. The switch is turned on by V2, which produces pulses, in this case 3 pulses of 5 volts. Each pulse is 1 millisecond. It's delayed by 10 milliseconds. The rise time is 10 microseconds and the fall time is 10 microseconds as well. The pulse appears for 1 millisecond and the period is 5 milliseconds. And we are doing 3 cycles and it looks like this. After 10 milliseconds we turn on for 1 millisecond and we turn off. Then at the 15 millisecond mark we turn on again and again at 20 millisecond mark. Now, having 10 volts and 100 ohms, we can easily calculate that that the maximum current that will flow through the circuit is going to be 100 milliamps. We can confirm that on our second circuit, that we have exactly 100 milliamps flowing through resistor R2 from the source V3. Now, from source V1, we use the same resistor and our switching transistor over here. So when the transistor opens, we expect to see 100 milliamps flowing through the resistor. As we can see, it's pretty close, but if we zoom in, it's actually roughly 98 milliamps. It's lower than we expected. Here we have the first property of the transistor that we need to be aware of, that it's not like a switch, it's not like a relay, because relay technically should have 0 resistance. It just closes the circuit, allowing the current to flow. Transistor will have some resistance between the collector and emitter, or drain and source. This property could be written in the data sheet of the transistor. This particular one does not, because it's not a power transistor, usually on the power transistors, that property is important because you're going to be driving big loads. There's going to be a lot of current. So the higher the resistance, the more power or heat will dissipate on the transistor. For that, you need to adjust and find proper heat sinks or proper way of removing that heat. That will also create a limit for your transistor. Now, if we measure the voltage on the collector of our transistor, we can see that likewise it does not go all the way to 0. If it was an actual switch, the voltage would drop to 0, and thus it would allow the full 100 milliamps to flow through resistor R1. However, we drop to only 160 millivolts, which is close enough. It can be considered that we're allowing this full current to flow, but in this case, since our transistor has some resistance, this is a voltage divider, not a switch. So very important, first, understanding that transistor is still a semiconductor in the circuit. There's still going to be some resistance. It's not going to be a switch. This is very important to understand. Now, this configuration of transistor is very typical, and this is what we call load transistor. The load is connected to the collector and emitter is connected to ground. Here we have the example of a high transistor, which means the voltage source, in this case everything is the same, right? 10 volts, same transistor, but the voltage source or current source is connected to the collector, while resistor R3, same value 100 ohms, is connected to the emitter. If your understanding of transistors is that they are just switches, the circuit should work the same. We should have 100 or 98 milliohms flowing through resistor R3. But when we measure, we see that we have less than half of that. Now, the reason that is happening is because to open the transistor Q2, our 5 volts needs to be in reference to the emitter of the transistor. That is another property of the transistors that you need to be aware of, especially when you're designing something, but it'll come in handy in power supplies and power converters. When we measure the voltage on the emitter and the voltage on the resistor R3, we see that the voltage dropped by roughly by half, 4.2 volts. That voltage is dependent on the voltage applied to base. For that reason, we can use transistor as a linear regulator. And this is something that you will see in many circuits, especially in pile devices, the amplifiers. They love to use transistors as linear regulators, utilizing Zener diodes to stabilize the voltage on the base and using emitter as a current source. As you can see, we're supplying our collector with 12 volts and applying 5.7 volts to the base, which causes our emitter to have roughly 5 volts, which means our resistor is gonna experience a 5 milliamp current flow. Now, why do we have to supply 5.7 to the base to have 5 volts on the emitter? Where is that voltage drop coming from? The easiest way to understand it is when you visualize the connection between the base and emitter as a diode. There's going to be roughly 0.6 voltage drop on every diode. Same on the transistor. Now, to solve our high transistor issue, what we need to do is connect the negative of our source to the emitter instead of ground. That way, 5 volts over here is going to be in reference to the emitter, not in reference to ground. And here's the important thing to know when you measure transistors, when you measure what kind of voltage is supplied to the base or the gate, it might not be in reference to ground, especially when it's high transistor. So in this case, our voltmeter says that we have 14 volts supplied to the gate, but what we're supplying is 5, because it's 5 in reference to our roughly 10 volts over here. That's why this is saying roughly 15. That allows full 98 milliamp current flow through the resistor. Our transistor is fully opened. Now here we have a little more real-world example. This is DC to DC converter, which works roughly on 50 kilohertz. What happens here is our high transistor opens, charging the L2 coil, which has 22 microhenry inductance. As soon as the Q6 transistor closes, the Q7 transistor opens, connecting the coil to the ground, effectively discharging it. This is very typical application of transistors, and normally you don't use bipolar transistors or transistors like this one. In this particular application, you use field effect transistors. We'll get to those. But just to illustrate over here, I use 2 NPN transistors and 2 sources. When this source goes up, this source goes down, and vice versa. As you can see, this one turns on for 6 microseconds at the period of 20 microseconds, while this one opens for 14 microseconds on the period of 20 microseconds, which means we have roughly 25% duty cycle. That in turn produces voltage of roughly 3.6 in this case. I marked it as 3.3 because I used 2 voltage sources. I didn't want to play around with it too much. But this is roughly what the typical 3.3 DC to DC converter will look like. And as you can see, we're using 12 volts as our input, and our output is roughly 3.3 volts. On this scale, you can barely see that it's not perfect 3.3. Now in reality, in practice, this will be 2 transistors, but I wanted to first draw it with 2 NPN transistors, not to confuse you. But more typical application is using NPN transistor and PNP transistor. And as you can see, we're still connected. This is our reference voltage, which we're measuring against the ground. So we see a lot of spikes, a lot of weird things. But the reason for that is that we're measuring against stable ground, while our reference voltage should be the negative of this power source V9. That allows us to control only one signal, to control the whole device with just one signal. However, the voltage that we're using is +5 and -5. The reason we need -5 is to fully open our PNP transistor. PNP transistor will work the same way as NPN, only in reverse. When we connect the base to ground, it will be open. If we connect the base to voltage source, it will be closed. So when the high signal is on our source V9, our Q4 opens and our Q5 closes. When the low signal is on our single source, the Q4 will close while Q5 will open, which allows us to more accurately produce 3.3 volts. And again, if we compare it to 12 volt input, it looks pretty good. roughly 3.3. Typically, in reality, our single source or single control source will be some kind of chip, some kind of specialized chip, which either will connect directly to the coil, L1 in this case, 22 micro, or it will have two transistors accompanied, and they will control the coil, and they will actually push the energy through the coil. Now, what's important to know over here, that if only one of these transistors catches a short, becomes a wire or low resistance resistor, it might not be immediately obvious. But if the high transistor catches short, if you connect 12 volts to the power supply, the 12 volts will go where 3.3 volts is expected, and it will fry the logic. If the low transistor catches short, the high transistor will likely also catch short the longer the device is on, because it's all the current is gonna flow through the low transistor when the high transistor opens. In this case, if our low transistor catches short and we open our high transistor, the low transistor will start conducting, and it will likely conduct all the way to the base, which will also open our high transistor, and it'll be continuous current flow regardless of our control signal, which is here. The best way to measure the transistor in circuit is obviously connect to collector and emitter, or drain and source, and to see what the resistance is. If your meter beeps showing that the transistor is shorted, it's not a definitive answer that this particular transistor is shorted. In many cases, our Q5 is actually two transistors, and this particular configuration of transistors is very common on motherboards, the computer motherboards, to control the voltages supplied to the CPU. That's why it's very important to check Q4 if it's not shorted, because if you connect your meter to 12 volts and to the ground, it might not tell you that there's a short, because Q5 is still working. Q5 is still not open, but Q4 is a piece of wire. Again, if you connect the CPU, supply 12 volts, all that 12 volts will go directly to the CPU, frying it in turn. So to sum up, our transistor is not exactly like a switch, and if your understanding of transistors is that they work like switches, like relays, you're gonna bounce off of these problems that I just showed you, and it'll be difficult for you to understand how the circuit works and why is it built the way it is built. Now, this short introduction will already cover a lot of faults and a lot of pitfalls that you might fall into trying to use transistors or trying to fix the devices. Even without the schematic and even without the board view, you will often see a control chip and two transistors and the coil. You will immediately know how this circuit works and how to measure it, how to test it, where to look and where to measure. Power supplies and power converters are essential part of any electronic device, because usually it is supplied with, say, 12 volts, 19 volts, 20 volts, and you have the logic that requires 1 volt, 1.8, 1.2 for memory perhaps, 3.3, 5 volts. All of that is produced from that base voltage. There's always a single voltage that comes into the device, and it needs to be converted into lower voltages. For that reason, those components, those parts of the circuit are most vulnerable to catching faults, catching shorts, basically not working. They are also the easiest to confirm, because all you have to do is measure the voltage. If there's no voltage, you measure the resistance. If there's a short, you measure the transistors. Maybe you can find the shorted transistor with just a multimeter. If not, you inject some voltage and see what's getting hot. What's shorted usually will get hot. However, we're gonna get to that, but sometimes it's not the component that is shorted that is heating up, it's the component that is protecting it that is getting hot. And that might send you on the wild goose chase. But we'll get to that. I think this covers the majority of standard use of a transistor and definitely shows you that it is not exactly like a switch. And with that, we're gonna finish the first session. I hope you guys enjoyed it. Thank you very much for watching, and I shall see you in the next one.